Okay, so welcome everybody to our Leeds Institute for Fluid Dynamics colloquium. Just a few housekeeping details. So Anne has very kindly said that if you have a question during her talk, you can ask it. So can I ask that you ask a question by raising your hand in Zoom? So you do this by going to the participants, clicking on participants. That will bring up a participants window. You then click on the blue hand and that will raise a hand, and we'll keep an eye on it and we'll let Anne know that there is a question for her. And we'll use the same mechanism at the end for asking questions as well. Just to say also, we're recording the talk. So if you want to stay anonymous, keep your video off. And if you don't want anybody to know you've been here, don't ask a question. So this video will hopefully appear on our YouTube channel at some point in the future. So it's a great pleasure to welcome Anne Juel today to give our colloquium. Anne is a professor in fluid dynamics and heads the Fluids and Soft Matter group in the School of Physics and Astronomy in Manchester. She was awarded a DPhil from Oxford in 1998, followed by postdoctoral positions at Texas, at Austin and in Manchester. She then joined the School of Mathematics in 2001 and then transferred across to the School of Physics and Astronomy in 2014. Anne is interested in very many aspects of fluid dynamics, interfacial flows. She did postdoctoral research with Harry Swinney on that. And her current research focuses on wetting, on complex flows, soft solids, interfacial flows and instabilities. And today she's going to tell us about bubbles in a Hele-Shaw cell. So thank you very much, Anne.
Okay, thank you, Steve. Thank you very much for the invitation. So the title is The Life and Fate of a Bubble in the Perturbed Hele-Shaw Channel. And you can see just one example of one of many videos I'm going to show you of a bubble that is started from rest and then propagated in the fluid within the Hele-Shaw channel. You can see that it has a transient evolution and it heads towards an ultimate long-term outcome. But before I start with the details of what we've been interested in, I can give you a couple of pointers to our group in Manchester. So I head the Fluid and Soft Matter group in the Department of Physics and Astronomy, and that sits under the umbrella of the Manchester Centre for Nonlinear Dynamics, and actually that's in its 20-year anniversary this year, and it's still going strong and has been built. It was the brainchild really of David Abrahams and Tom Mullin, and it has been built on an ethos that involves a combination of cutting-edge theory and quantitative experiments. And we have quite a vast array of activity going on at the moment that involves fluid structure interaction, wetting, complex fluids and soft solids, microfluidics, and what I want to talk about today, which is essentially nonlinear dynamics. Okay, so the project I'm going to talk about is a collaboration between experiments and theory, and the people involved are here on this slide. So the ideas for this project were developed during Andres Franco Gomez's PhD. And then Grégoire Lemoux spent a relatively short time with us and built a superb experimental setup. Then Antoine Gaillard, aided by an internship student, Grégoire Lelay, did some really highly controlled experiments. And then I'm going to show you a set of numerical simulations that are the work of Jack Keeler in collaboration with Andrew Hazel and Alice Thompson. And a lot of what I'm going to talk about is in a preprint that is on the archive. I'm going to dominantly focus on the experiments. There's a lot more than I'll have time to say about the numerical simulations, and there's actually another paper in preparations on the dynamics of multiple bubble systems. Okay, so the starting point of what I want to say is really from the experimental point of view. So in experiments, an experimentalist tends to look at long-term behavior in fluid flows. So for instance, if you take classical fluid systems like the Taylor-Quette system, You look at Taylor vortices or wavy vortices. You might look at steady convection cells in Binar convection, or in a system where you displace oil in a quasi-two-dimensional channel, you may look at the steadily propagating air finger that appears at long time following the Safman-Taylor instability. Now, when we see steady or periodic flows, we can infer that these are stable solutions of the underlying governing equations. And one way to understand the dynamics is to look at these systems are, fluid systems are obviously nonlinear, and is to look at the bifurcations between stable states, ultimately loss of symmetry of the flow, and transition towards some form of disorder and complexity. The point is that experimentally we tend to ignore unstable flows. And the reason for that is really because we say, well, we can't see them in experiments, but that's not totally true, because in principle we can see them or glimpse them fleetingly, but when we look at the transient evolution towards a steady state. Okay, and so transient evolution is really the focus of this talk, because unstable state very strongly influence transient evolution, and that becomes particularly significant when the flow is so disordered that there are no apparent stable or periodic states. And so what we wanted to do with this, these sets of experiments, was to explore transient evolution, and thereby how a system selects its stable long-term dynamics. So again, I can show you another movie of a bubble, and this is going to do something different than the previous one. Here the bubble breaks into two, and eventually you end up with a long-term state where you have a bubble and a compound bubble that are moving on either side of the channel, each steadily moving, but separating because the leading bubble moves faster than the trailing bubble. Okay, so the thing maybe to say at this point is that the reason we're interested in transient evolution is really that in many practical situations we'll never get to the stable states, and we might only be interested in how the system evolves transiently. So just a little bit of history on the sort of connections between fluid dynamics and dynamical systems theory, really. There are these connections were made very early, and they arose from the desire to understand complexity and disordered flow. And this is a very partial history, by the way, but a notable sort of milestone is the identification by Juel and Tarkens in '71 of turbulence with deterministic chaos. And then following that, the first observation in a fluid flow by Golub and Swinney of a transition to chaos, and that was in Taylor-Queck flow. So in that type of flow, you have significant spatial confinement, and that means that a small number of dominant eigenmodes will control the dynamics. Now, if you now relax these spatial constraints, then that naturally will give you very much an increased number of significant eigenmodes, and that will be associated effectively with a reduced theoretical understanding of what's going on. So in recent years, however, so basically you could say that the bottom-up approach there kind of comes to a dead end in terms of understanding complexity in fluid flows. But in recent years, however, there's been a rekindling of interest in dynamical systems ideas because of considerable success in elucidating the subcritical transition to turbulence in shear flows. And here I've written down a number of names of researchers who've worked theoretically on this problem. There's also a vast amount of experimental work on this problem that I haven't included here. Essentially, the idea is that we they choose to reduce the dynamics of sort of fairly weakly confined open flows to a small number of invariant objects in phase space, and these are known as edge states. So these may be stable, unstable, steady, or time periodic solutions of the equations, and they're manifolds. They could be chaotic attractors. But the key point is that any form of trajectory in phase space, or so any form of evolution effectively of the fluid flow, cannot cross these invariant objects. And because of that, they compartmentalize the phase space. And the most famous of these is the edge of turbulence, which separates the regions of phase space where initial conditions lead to eventual decay to a laminar state again, from those where the flow becomes fully turbulent. Okay, so these ideas are fairly complex, and actually the edge states are typically not easily determined because they tend to be extremely high dimensional in complex flows. So I find a useful conceptual picture of an edge state. You could think of a stagnation point flow, or equivalently in sort of dynamical systems parlance, you could talk about a saddle point. So the stagnation point itself is an unstable fixed point, and then the important invariant objects here are the stable and unstable manifolds. These are simply the dividing lines of the stagnation point flow. So essentially, these the ultimate fate of a fluid particle will depend on its position relative to these manifolds. And so you can say that these manifolds are essentially the edge states of the system. And in this case, there's a stable direction that pushes you towards the fixed point, and one unstable direction that takes you away from the fixed point. But in more complex flows, you might have essentially many, sort of in a weakly unstable fluid flow, you might have many stable directions and only one or two unstable directions. So essentially, during transient evolution, you can spend a lot of time near some of these saddle points. So what we wanted to do is to look to explore these types of ideas on a flow that's simpler than turbulence. So you may ask, why choose a bubble in a Hele-Shaw cell? And one thing that's really nice about bubbles propagating in Hele-Shaw cells, so Hele-Shaw cells or channels are essentially typically have an in-plane dimension, so width, for instance, of the channel that is much larger than its depth. So they're quasi-two-dimensional. In these systems, the most important system information is encapsulated in the shape of the interface alone. And so, in a sense, what you see is what you get. And they're also simple enough, because they're quasi-two-dimensional, to be modeled by two-dimensional numerical models. And so, for low enough flow rates, the edge states in these systems are going to be just the weakly unstable modes of the bubble propagation. But there's an additional twist, and you've already seen that in one of the videos. The bubbles break off, and that's going to add considerable depth to and degrees of freedoms to the problem. Now, however, even though this type of this is a very simple flow in many ways, it is nonlinear, and it also contains much complex dynamics, and that's not necessarily understood. And so let me just sort of say a few words about the sort of complex dynamics that you encounter in these systems. So you can look, for instance, at the very classical fingering in a radial Hele-Shaw cell. So in this case, you're injecting air into an oil-filled channel, Hele-Shaw channel, from a central point in the cell. And what you're seeing, and what people describe typically, is that the interface is unstable, and then it leads to the formation of fingers. These grow, the tip split, then the fingers compete, and then the tip split again. And so there's a whole succession of unsteady dynamics going on. But so I would argue that this is disordered front propagation, and you could say, well, the aspect ratio of system is pretty small, so how do you know? But if you move to much larger cells, you find that you can get fractal growth exponents for these types of complex patterns. But it's not really looked at from a dynamical systems point of view. And really, if you think of viscous fingering in a channel like that, well, okay, the interface growth is typically disordered, but actually there are known self-similar fingering states, and they would look a bit like those in these images. So these were obtained in a situation where these self-similar fingers are stabilized, but in the system I've just shown you in the classical Hele-Shaw cell, then they are generally unstable. So you have underlying this unstable front propagation, you have a whole set of unstable solutions that you don't typically see, but which are there. And so you can then start asking, well, how do they affect the front propagation? And so what is actually the dynamics, dynamically, what is the disordered front propagation? And that, to my knowledge, has never really been addressed. Okay, so the problem with this system is that it's pretty complicated because everything's disordered. All the propagation is transient, and you can't actually start from a nice, stable, simple sort of, say, steady solution to look at then how it bifurcates to disorder. But you can do that in the channel. So if you do the same type, look at the same type of flow but in the channel, so now rather than injecting from the center, you inject from the end of the channel. So you inject air that displaces the resident oil in the channel. Then essentially at long time, you get typically a steadily propagating finger, and that's a sort of Safman-Taylor finger. And what we know is that this finger is linearly stable for all values of the driving parameter, the known Safman-Taylor parameter, and that is based essentially proportional to the flow rate you impose, and depends on both the aspect ratio, so width over depth of the channel, and the capillary number, which measures the ratio of viscous to surface tension forces in a channel. So theoretically, it should be stable for all values of this parameter, but actually in practice, you see that the system goes unstable to tip splitting at a finite 1/b threshold. And this threshold depends on the level of roughness of the channel. And that's very reminiscent of the classical sort of Reynolds pipe experiment, where you get the transition to turbulence through a subcritical transition, which also depends on the level of perturbation in the pipe, where quasi-flow loses stability to turbulent puffs. But here, the transition, to my knowledge at least, the transition scenario is completely unknown. Okay, so that's quite a lot of complexity for such a conceptually simple system. Okay, so here we didn't want to start straight away. You jump in at the deep end and look at the disordered front propagation. What we decided to do was to investigate these dynamical systems ideas on a simpler system. And for that, we chose to look at a bubble propagating in a Hele-Shaw channel. One of the reasons for that is that it's easier to look at a bubble than long fingers numerically. But also, we then perturb the Hele-Shaw channel with a small rail, which you can see here along the length of the channel, and which is makes a depth perturbation of about 2.4% in our case. And then we propagate the bubble by imposing a constant flow rate. So the main governing parameter in our system is going to be the flow rate, the non-dimensional flow rate, which is akin to a capillary number. And then we're going to fix the rail size and all the geometric parameters in the channel. Why this is a useful system to look at is that it has a very rich solution structure, and we can calculate all these solutions numerically. We can calculate both stable and unstable, say here steady solutions. I don't want to go through this. This is a steady bifurcation diagram of the system. I don't want to go through it in detail. Suffice to say that you have several stable solutions that you may see long-term in the experiment, and a whole host of unstable solutions that may also influence the transient dynamics. And in that respect, the advantage of this rail is that it sort of enriches, in a sense, the solution structure. Okay, so that's that's essentially the system that I'm going to focus on from now on. So because we wanted to study transient evolution, we needed a very long channel, and that's where Grégoire Lemoux did a fantastic job in building this system. You can see some pictures of it. We have essentially an injection system. We have a part of the channel that we use to center the bubble. That is created upstream here through this air valve here. We create the bubble, then we center it, and then we let it go down the channel. And we drive all this with syringe pumps. And what is worth looking at in these pictures, you can see the illuminated channel, and then you have a camera system on the rail above it, and the camera moves with the bubble. It doesn't track it sort of in real time, so we set a given speed of the camera, so that's why you'll see in the movies of our bubbles, they might be look like they're moving slightly forward or slightly backwards, and that is really relative to the motion of the camera, but we can calibrate that out. So the other thing that's worth saying about this experimental setup is that this is a very long channel, but the features are extremely well controlled. So geometry is extremely well controlled, and that's the reason we're able to get these very systematic and reproducible experiments. And I'm saying that because as we increase the flow rate, we're going to see that we lose reproducibility. Okay, so we can set a bubble going in the channel with a constant flow rate. The other parameter that's going to be important to us is, because we want to look at the transient evolution of a bubble, is that we want to give it an initial shape and start it from rest. And then we're going to limit ourselves here to centered initial bubbles, like you see in the diagram here. And we're going to parameterize this centered initial bubble by its width. So how do we set different initial conditions? Because we want eventually to look at the effect of the initial bubble shape on its transient evolution. And to do that, we're going to, early on, so upstream in a channel, we're going to start the bubble going, and then it's going to deform into slender bubble. We interrupt the flow, and we let the bubble relax to different bubble widths that we can then track on this graph down here, and we can essentially calibrate the relaxation of the bubble so that we can reproducibly set the same initial condition over and over again for different bubble widths. And we have obviously a limited range within the relaxation of a bubble of a certain size. We will only look at a single bubble radius, so a single bubble, you could argue, volume in all the experiments I'm going to show you. And it's essentially this one here that you see in B. Now, I'm brushing a lot of things under the carpet here in terms of the experiments, because there are compression effects, there are thin film effects that depend on the flow, and all of these have been taken into account. And I will just sort of, to keep it simple, I will ignore all of that in what follows. Okay, so what can we start by doing? Well, we can start by varying the initial bubble width, D, at a constant flow rate. And so we choose an intermediate flow rate, And then we're going to let 2 bubbles go, a slender one and then a wider one. And you can see that these 2 bubbles do really rather different things. So the first bubble deforms, but then it remains a single bubble and eventually adopts a sort of on-rail, asymmetric, long-term behavior that is steady. The other bubble breaks in 2 and then never recombines, so you end up with 2 independent bubbles, essentially, that are each moving steadily, but the larger one is moving ahead. And essentially, that means that they are indefinitely separating. And so it's important to take a moment to think about that. Basically, these bubbles are going to separate indefinitely. They become very quickly independent of each other, and they do not form a 2-bubble steady state. Okay, so clearly at this flow rate we have a single bubble steady state available, but when the bubble is wide enough, we're not able to reach it, and we get to something really quite different as a long-term outcome. So what actually happens in the detail is that the bubble deforms over the rail when it's narrow. So it's pulled forward. So you have a tip that's pulled forward over the rail. The bubble deforms. It remains symmetric for quite a long time, and then in the latter part of the evolution, it just shifts to become this to reach the sort of on-rail asymmetric state, which is one of the available steady states of the system at that flow rate. In the other case, we have the bubble breaks in 2, and these bubbles never rejoin, and instead they continue to travel. They relax and continue to travel on either side of the rail. So in a sense, you could say that the deformation in the wide bubble is kind of exactly opposite to deformation in for the slender bubble. And you can explain these different deformations, at least qualitatively, in terms of the fact that there are local variations in viscous resistance across the channel and surface tension forces, and depending on how much of the bubble sits on either side of the rail, you can get different deformation. But really here, what we are interested in is looking at, what makes this transition between ending up with a single bubble and ending up with 2 bubbles. So what happens in between? And so what happens in between, what happens in between is essentially a combination of getting this tip here forming over the rail and these tips forming on either side of the rail. So we're going to get triple tipped bubbles. And so you can look at this for 2 intermediate bubble widths, and you can see that now both bubbles break in 2, but one of them recombines, where all the products aggregate back together, back to a 1-bubble steady state. Oops, it's jumping around a lot. Back to a 1-bubble steady state, which is this on-rail asymmetric state, very similar, but now we have a compound bubble instead, and very similar to previously. And for the second bubble, we have a breakage that leads to 2 separating bubbles. And so if we look in the detail at this, we see that there's a competition between these middle and edge tips of the bubble. And so if the middle tip grows faster, then you end up with an evolution that leads you back via changes in topology to your original bubble system, albeit a compound bubble, but at long times these will coalesce back together. And in the second case, where the bubble width is marginally wider, you have the edge tips that grow faster than the middle tip. And in that case, you get a sequence of 2 breakups, and eventually the bubbles do not migrate across the rail, remain on either side of the rail, and you get these compound bubbles that are essentially separating from each other. What's interesting here is that it's clearly the early time evolution that determines the long-term fate. And what's also interesting is that you're going through all sorts of topological changes, but you get back, in some cases at least, to very simple outcomes. So what we did until now was to vary the width, the initial width of the bubble at constant flow rate. But now we can look at varying the flow rate at constant initial bubble width. And so we take 2 bubble width, sort of the slender bubble, which is the one on the left, and the wide bubble, which is that on the right. And you can see that at very low flow rates, then you find that essentially you can't really distinguish between these evolutions. They evolve exactly the same, whether the bubble is slender or wide. And what you end up with in each case, so this is a time sequence. What you're seeing here horizontally, you see time sequences of bubble evolution from these pink frames, which corresponds to the initial condition. And what you see essentially is that you end up in both cases with either a single or a compound bubble, which are something we call off-rail bubble, because the majority of the bubble sits off the rail. It's asymmetric, and the majority of the bubble sits off the rail. And that happens to be the only stable, steady one bubble state at these values of flow rate. But now, if we increase the flow rate, then we get more steady bubble states that become available. And in particular, we can have an on-rail symmetric bubble. So the question is really, let's increase the flow rate beyond this. What happens then? Does the system then eventually reach the system eventually able to settle on this symmetric bubble? And so we can see, so we can look at both slender and wide bubbles again. And for the slender bubble, indeed, that's exactly what happens. You deform the bubble transiently, and then it lands on the symmetric bubble state. And that's this on-rail symmetric long-term behavior, which is which is steady. Now, for the wide bubble, however, this doesn't happen. Even though this state is available, and also the off-rail state that we had before, the system chooses to do neither. It actually breaks up and ends up as 2 separating bubbles. And this is neither a steady state of the one bubble system or a steady state of a 2 bubble system. And then we can look beyond that and increase the flow rate further. And in that case, what we see is that for the slender bubble, we actually go through essentially relatively simple evolutions. And we end up with bubbles that are either simple or compound, but which follow the available on-rail steady states in that system as the flow rate increases. So the behavior is very predictable, but is very predictable and sort of kind of what we would expect. Now, for the wide bubble, however, we never reach any of these stable states that are available, and instead we always break up into 2 bubbles, 2 separating bubbles. So the last thing to look at is really, as we increase the flow rate significantly, we see that the early time evolution is always robust and it's symmetric. We started from a symmetric state, but the late time evolution is the one that leads to tip splitting and essentially cycles of splitting and coalescence, the larger the flow rate. And so in that, so what we're going to see is that this is going to introduce sensitivity, possibly extreme sensitivity to initial conditions. So we can take all of these sort of experiments that I've shown you, and we can sort of summarize them in a sort of phase diagram where we're plotting the flow rate on the vertical axis and the initial bubble width from slender to wide on the horizontal axis. And these are, all these symbols correspond to all the experiments we did, and we have sort of fairly arbitrarily, really, sort of classified them according to the initial early time deformation when we set them into motion. And we get a whole lot of different symbols corresponding to different early time evolutions. But if we ignore now the points, the exact points on the diagram, and just look at the background colors, the background colors tell us about the long-term outcomes of these bubbles. So, for instance, you get off-rail bubbles when you have low enough flow rate. That's what we saw in the previous slides. And then at some critical flow rate, you start getting two separating bubbles. That's this red area. And for the more slender bubble, you can retain one bubble long-term behavior. That's the green area. But actually then, essentially, when you go to large enough flow rate, you start having this late tip splitting that comes in. And that can lead to this yellow area, which means essentially that you get either one on-rail bubble or two off-rail bubble, and sometimes more than two. And what we see is that as we increase the flow rate more and more, we get increased sensitivity to initial conditions. So you can ask, well, what is it that selects this long-term behavior? Okay, and so for that, you have to kind of move, or that's where we move to the depth average lubrication model that we can compute, where we can perform numerical simulations of both of the transient behavior of our bubbles and try to understand what these dynamics correspond to. So the depth average lubrication model comes from the 2D Hele-Shaw equations, which are a depth average version of a reduction of the 3D Stokes equations. And we have a prescribed depth perturbation in the cross section of the channel, which is this B of y. And so B of y is the local depth of the channel. And you basically, what this model does is that it separates sort of viscous effects, the effect of the depth perturbation due to viscous effects, which comes into the bulk equation, from the surface tension effects. And the surface tension effects come essentially through the normal the dynamic boundary condition. And the dynamic boundary condition here includes the effect of the cross-sectional curvature, which in our system varies as you go across the channel and as you hit the depth perturbation. So essentially, it's a sort of slightly generalized Hele-Shaw equations where the depth of the channel has a prescribed spatial variation. Okay, and you can perform numerical simulations of this, and these have been implemented in the open source library umflib. The mesh deforms with the interface, and here the particular methodology that we use is for being able to incorporate breakup and coalescence. And we don't incorporate any physics really of breakup and coalescence. We just decide to snip the interface when the film thickness goes below a specified threshold, and then let the two products, bubbles, relax due to capillary pressure gradients in particular, and the flow. And this works very well in order to just pick up sort of the breakup effects that we see in the experiment. For coalescence, it doesn't work quite so well. We do the same thing below a certain film thickness. We merge the two approaching or aggregating bubbles. But here the coalescent process is very rapid. That is not the case in the experiments where you saw these compound bubbles that last for quite a long time. So we clearly don't pick up, or don't even attempt to pick up thin film dynamics here. But we have a whole sort of panoply of tools at our disposal, which include direct time simulations, steady state calculations, linear stability calculations, and also edge state tracking. And oh, that's what I wanted to show you. So I mixed up my slides. So what's really remarkable, I think, is that this very simple model picks up pretty much everything we see experimentally, qualitatively. And so in particular, you can pick up for a more slender and less slender bubble, you can pick up the fact that the bubble long-term remains a single steady state, or the bubble long-term ends up at two separating bubbles. And you can pick up essentially the whole same sort of transient evolution phase diagram that I showed you experimentally before. But what we can do now is try to understand some of these transitions. And I'm not going to go through many of these in detail, but I will show you. So for instance, we can look at very low flow rates. We can certainly look at how one bubble unstable states determine the transient evolution. But the one I want to focus on is that boundary between long-term one bubble states and long-term two separating bubble states. What is actually going on? And so for that, I'm going to show you a movie. And this movie is going to be for the same initial bubble width. And this initial bubble width, so we're going to start with one bubble. We're going to let it go at a relatively low flow rate, which happens to be below the threshold. So it's at 0.02, it's down here. And we're going to look at its evolution. So it's going to break into two, and there we're now going to put on the unstable two bubble steady states that exist in the system, and how the bubble evolution is going to negotiate these, its way around these unstable states. Oops. So starting with the low flow rate, you can see the bubble breaks up, and then you have an edge state, this green, and it effectively goes and sits on this edge state for a while before it carries on its evolution. The edge state is unstable. And you can see that what it does in the experiment is pretty much the same as what it does in the numerics. Now you move to a higher flow rate, but you no longer have only one edge state, you have two edge states. So it sits on the edge state 1, but actually it's prevented by edge state 2 from coalescing. And essentially you end up with separation instead. So we can look at a summary of this, where you have a time evolution of these bubbles. So the first bubble at the low flow rate, below the threshold, you only had one edge state. The system sat at this edge state for a while, for quite a while, and then eventually gets kicked off it because it's unstable, and then evolves to give you, to basically where one bubble goes across the rail and coalesces with the other bubble to give you one bubble long-term behavior. Whereas in the second case, where we're at a higher flow rate, you now have a second edge state, and that edge state now prevents you from, prevents the bubbles from crossing the rail and coalescing, and forces the bubbles, the two bubbles, from separating indefinitely. And so you can see that edge states are essentially driving the dynamics here. Okay, so that means that these types of ideas can bring some understanding, or sort of bring some understanding to the sort of transient behavior of a relatively simple system like this one. But earlier on, when I showed you the experimental diagram, I also pointed out that as you increase the flow rate sufficiently, then you get sensitivity to initial conditions. And this is where things get tricky. And I can show you some movies of this in the experiment. So what you're looking at here is 5 repetitions of exactly the same experiment. Let's see if I can run it again. Whoops. 5 repetitions, exactly the same experiment, same initial bubble shape, same flow rate. And you end up with totally different evolutions. And if you look at the final products, you have 5 totally different final products. So you can get an oscillating bubble in one case, compound bubble. You get 2 separating bubble, apparently stable bubble in one case, in this purple case, and then you get sort of fragmentation of bubbles where essentially the main bubble reaches some form of steady state, but it's losing volume through small pieces that are being left behind. And interestingly, this type of sensitivity occurs both in the experiment and in numerical model. It's really there in both cases. In the experiment, we can track it back to both channel roughness and initial condition. And you could argue that, you know, all these simple arguments we've made about edge states so far have been about very simple, sort of unstable, steady states of the system. So, for instance, 2 bubble states that prevents the bubbles from coalescing back together. But of course, as you go to higher flow rates, this edge, the complexity of this edge is likely to increase tremendously due to the increasing number of bubbles in the system and also the increasing flow rate. Okay, so to some extent there, that leaves us with an inherent unpredictability in this system that, again, can be rationalized in terms of the underlying sort of invariant objects in the system. So I'll conclude by just recapping essentially what I've been trying to tell you. So I've been trying to convey some basic sort of nonlinear dynamics ideas and apply them to a simple bubble flow in a geometrically perturbed Hele-Shaw cell. And what that system is that it's remarkably rich in dynamics despite its conceptual simplicity. And in particular, what that means is that we can put together a very simple depth average model that we can really explore extensively numerically, and that captures much, if not all, of the dynamics qualitatively rather than quantitatively. In this system, the topology changes are clearly key to the dynamics. And we find that weakly unstable solutions or edge states divide the phase space between different dynamical outcomes, and that the long-term fate of the bubbles can be very sensitive to initial conditions. So that has some fundamental consequences for predictability in the system. So with that, I will stop. Thank you for your attention. I can't hear anyone.
Hello. Okay, sorry, we had a bit of problems with unmuting there. Thank you, Anne. Thanks for a really interesting talk. We have time for some questions. We have a couple of questions already. So,
sorry, did you raise your hand during the talk? I just didn't see.
No, nobody raised their hand during the talk. They've been saving themselves for now for the opportunity. So our first question is from Prashant.
Okay.
Can you unmute yourself and ask your question?
Hi, Anne. This is Prashant Valuri from University of Edinburgh. Very, very nice talk. So I'm really keen to know. You rightly mentioned about the topology changes being key to the dynamics, and in your experiment, I think you had a strip type which was actually causing the topology change, if I'm correct, right?
Yeah. Yes. Yeah.
And so what is the dependence upon the topology chain? So if you had a bigger strip, if you had a fatter strip, for example, or if you had a thicker strip, how would that change? So obviously, is there a way that you can probably capture the roughness? So for example, rather than having a strip, if we change, if you have the height of the strip as certain x, and basically you can have some kind of a roughness parameter there. But if you have a kind of another strip, which is a bit more wider, but ultimately having the same roughness.
Yeah, so it's a good question. So the in a sense, it's sort of so as I mentioned earlier, the inherent disorder in these bubble flows come from the roughness in the channel ultimately, and actually the wider you make the channel, the more sensitive the system becomes to roughness. And that's a feature of this type of flow. But so in principle you could play around. So you could play around with these strips to make roughness. Although I think that ultimately, if you want to look at the effect of roughness, I don't think that's necessarily the best way to do it. In our case, we have got this strip because it stabilizes some types of modes that would be unstable in the regular Hele-Shaw cell. And because we wanted to look at how the system selects its final outcome, we wanted as many stable states as possible. It turns out that actually what the system chooses to select is to go completely out of any of these stable states and break up in multiple bubbles. Yeah, so I don't know if I'm answering your question.
I think partly, but if you had, from what I understood from your figures is basically you have the strip which is at the bottom of the channel.
Yeah.
And what would happen if you had a strip at the top of the channel as well? So you'll have a symmetrical roughnesses.
Yeah, so we haven't done that, but again, I suspect so. I think that you would enhance. So if you make that strip much thicker, you will basically evolve the steady state solution structure of the problem, and so you will get different types of stable solutions, and so essentially you will actuate the underlying solution structure, and that will actuate the transient evolution by as a result. If you put a strip right on the top of the channel, you probably all you would do probably is just have a cumulative depth perturbation that is thicker, but potentially you could have lots of these strips side by side, and you could use these strips to make the bubbles jump over the obstacles, because they can jump onto certain conditions but not other conditions. So potentially there's something interesting to be investigated there. Yes.
Thank you.
Okay, thank you. Now our next question is from Sarah Smith. If you unmute yourself and ask your question.
I can't. Oh, there we go. Thank you. Thank you for a really great talk. My name is Sarah. I'm from Portland State University in the US. This is all very new to me, and I was wondering if you could comment a bit more on the difference, I guess, going from asymmetry and the low flow rates for a single bubble diameter, moving into symmetry with those moderate flow rates, and then going back to asymmetry, and what your insights from that are.
Yeah, so in that case, I need to, so if I go back, I didn't actually detail, so I didn't detail what the system would do, but if you look at this diagram here, on the in the lower left of this slide, then these are the sort of steady solutions of the system, and the sort of solid lines are the stable solutions, and the dashed lines are the unstable solutions. And you can see that, for instance, so initially you will start with a symmetric bubble at very low flow rate, and that will bifurcate to an asymmetric bubble. And then for a while you don't have any symmetric stable bubble, and then you regain some symmetric stable bubble. To my knowledge, that I don't have a simple hand waving mechanism to give you to explain exactly why that happens. It's a these are finely tuned balances within that system. So unfortunately, there's another thing that I've glossed over very happily in the talk, which is that the bigger bubble always moves faster than the smaller bubble. Again, it's something that we have looked at extensively, and we do not have a very simple, I mean, there's a long explanation I could provide, but I don't have a simple hand-wavy mechanism for explaining why that is. So, which is why I've sort of glossed over this in a way. Does that? Sorry. So not very satisfactory, but in a sense, it is the result of there's a complex sort of set of steady solutions, or steady basically modes of bubble propagation in this system that we see both experimentally and numerically.
That's very cool. Fun to keep working on. Thank you.
Thank you, Sarah. I have a naive question, Anne.
Yeah.
Are all your edge states steady?
No, I suspect not. Well, I can tell you that they're not, actually, because there's one that we have investigated. That's in this paper, Juel et al., PRSA, where actually the edge state is, so right here, there's a subcritical Hopf bifurcation. And that, there's a really interesting thing going on here, because if you place yourself somewhere, you start with yourself on this symmetric bubble branch here, but very close to the Hopf state, and you perturb the bubble, you have extreme sensitivity to the type of perturbation. Basically, you'll kick yourself off onto the unstable limit cycle, and from there you might reach the asymmetric solution, a two-bubble state, or go back onto the symmetric solution. And that unstable limit cycle that emanates from the Hopf is actually an edge state as well. I suspect there are many more, much more complicated edge states in the system as you increase Q. Yeah. But we've stuck with the very simplest one. But it kind of gives you an impression that you can start from very simple sort of principles with these edge states and see what they do in a very simple way before trying to extend to more complex. We can track them, by the way, numerically, like they can be done in 3D Navier-Stokes. Yeah.
Okay, thank you. Okay, so we have time for one more question. Dwight, would you like to ask your question?
Hi, Anne. Thanks. That was an interesting talk. So much of I actually had several questions, but they're mostly already been asked, so that'll save time.
Okay.
But let me just try and ask, you seem to not want to answer it. Well, why does the bubble want to hug the edge, the asymmetric ones? Do you have some sense of that?
Oh yeah. So yes, that first. So sorry, I was a bit okay. So thank you for pushing on that, because of course, so typically in the unperturbed channel, you have a bubble that moves down the middle. Yeah. But actually, there's a degeneracy there. It could move down any part of the bubble, of the system, but it tends to sense the walls. But now, so you start with, say, a symmetric. So let's put a symmetric bubble going. If it's large enough, it tends to sense the walls. But if you start with a symmetric bubble, let's say, then, and you have the strip along the channel, then of course you have increased viscous resistance over the strip. And then you have reduced viscous resistance on either side of it. So for very slow bubbles, it's fine to keep traveling over the strip, but at some point, as you increase the non-dimensional flow rate, i.e. the ratio of viscous to surface tension forces, it will become favorable to move sideways to the regions of lower viscous resistance. So that's essentially the reason behind. But actually, you have to be careful with these arguments, because in the unperturbed Hele-Shaw channel, you also have asymmetric solutions. You just happen to be unstable. And all of these solutions already exist in the unperturbed Hele-Shaw channel.
Can I just ask something, if it's okay with Steve, just real fast? If you could just flash to your slide where you showed the two different kinds of edge states with the dashed lines. This will be a quick question, I think.
Yeah. So the ones with the two bubble edge states.
Yeah. So the question is, did you compute those by putting half the bubble volume, looking for a solution that had half the bubble volume in two patches and looking for equilibrium of that kind? Is that was the condition you put? Okay, fine.
That's right. So these are two bubble systems. So you're constantly jumping between different systems because you change the topology.
Sure,
and
sure.
so
But for the edge state, you impose that condition. Is that what you did?
That's right. You look at two bubble systems with a certain volume ratio. Yeah.
Okay, fine. Thank you very much.
Yeah.
Good to see you.
Okay, thank you, Dwight. Okay, so this really is the last question. Sorry, and we have one more. Is it Regin?
Yes. Hello.
Hello. Go ahead.
Yes, sir. That talk was very nice. I am from India, National Institute of Technology. So this topic is actually somewhat new to me, but my question is that whether the strip the madam was talking, so have you put different roughness strips? Because if we change the roughness, the bubble will also, evolution of bubble will also change. So have you put the different kinds of strips measuring the roughness parameters?
So we have tried to make the channel as smooth as possible. Both the strip that we put into the channel and the channel itself, we have tried to make as smooth as possible, because as you increase the flow rate, you do become sensitive to roughness. We also have done experiments that I haven't shown here by actually controlling or attempting to control roughness in the channel to look at the sort of more a transition to disordered from propagation, and we do that in quite a different way. But here, no, we have not varied the roughness in the sense that we have both the strip and the channel are as smooth as possible in order to try to keep things as clean as possible.
Okay, one more question.
Dynamics. Yeah.
What about the instabilities, whether the KH instabilities and those kinds of things, how it will change?
Sorry, could you repeat the question? I didn't.
So the instabilities, whether it is Kelvin-Holtz instability or Taylor instabilities, those will come into picture.
Yeah, so I'm totally glossed over this altogether, but this is a zero inertia system.
Okay.
So none of these are so we are talking about Stokes equation. I did say it very briefly, but I didn't actually emphasize that. It's really, you could think of it as essentially a zero Reynolds number system. All the nonlinearity in this system comes from the presence of the interface, not from the fluid dynamics.
Okay.
Not from the bulk fluid dynamics, let's put it like that.
Okay. Thank you so much.
Okay, thank you, Regin, and thank you, Anne. Before we go, I'm going to hand over to, let's thank Anna. I'm the only one who can clap, I guess, but thank you very much. I'm going to hand over to Sepida, who's our colloquium organizer, who